so I don't feel guilty, but I'm going to record the session now. And basically welcome everyone again to this joint workshop on the stream media and immersive scene description together with Khronos, 3GP, and MPEG. We had a session yesterday and there's a session today. Very quickly, today I checked we had about another 30 to 40 registration. So welcome everyone being back or being new today. For those being back, we can go, you maybe can skip a few aspects, but we have a motivation slide, you can look it up, but mostly the idea comes from two effects that we had in MPEG. We developed some Khronos extension. We looked through those yesterday and wanted to reach out to get some first-hand comments and discussion on the glTF extension. Secondly, there's the broader approach to look what's happening in other organizations with respect to immersive media, Khronos, MPEG, and today also we get at least a short overview of what's happening in 3GPP. Considering this as a starting point, and again, I say thanks to Neil and Frederick from Khronos and 3GP of supporting this workshop. There's a couple of logistics, and I repeat just the most important issues we're recording. So if you have a problem, let me know now, but otherwise we keep this as something that is available for the organizations and likely also for public. We ask you to adhere to the MPEG edit group policies. I encourage to use Zoom features, chats. I also applause. Please use raise hands as needed. I also encourage to use the chat for discussion. I think that worked well yesterday. Put in questions that you would like to ask, discuss along things or do clarification in there. We also have the online minutes that are available, and the link is in the chat. I'm going to reshare it again if you missed the chat and joined late. So this is mostly said here. Importantly, on this link, you would also find this presentation, or at least the version from yesterday, which is the same, except some updates I did just recently. And secondly, you'll find also all of the linked presentations there from yesterday, and I will also add those from today as they come available. Maybe also asking, can you please change your name, at least to have a first and last name and the affiliation. I'm going to do this on my end as well in a few seconds. Okay, we had yesterday a program and an agenda of day one where we talked about glTF and MPEG scene descriptions. Two presentations, both are linked, good discussions, and then we looked into the implementation, support, and tools. We had three presentations. Rob is still going to collect his videos and make it available today. So all three presentations are available, and also discussion is available in the online minutes. Quick summary. Yesterday, I checked the meeting records, and we had 186 attendants in total. They were coming in and out, but I think we had a stable 130, 140. Great. Well, I think what we identified for glTF and MPEG scene description, that we view the MPEG extension as vendor extensions. Also from the IPR perspective, there was some discussion here. Khronos glTF core specification KHR extensions are available on the Khronos royalty-free IP policy. That was an important point to be stressed. We also looked at the technical aspects, and that the glTF extension, both organizations are considered complementary. So we didn't see anything that we say we're doing the same aspects at the same time. So, but still, it's good to continuously check this. On implement and tooling support, what we basically looked into industry presentation points, mostly to challenges in handling large amount of data efficiently and securely. So that was what Rob Conan pointed to. And this is where standards would be needed. But generally, one should be careful to find a balance between what is an application and what is an implementation domain and where you need interoperability. So a continuous check of these issues should be done. MPEG and Khronos maintain tools to support implementation. There's quite some resources available. Look into the slides. But the promotion, accessibility for broad, and also the maintenance of these tools is a major challenge. So it requires either volunteers or fundings and so on. So everything like this obviously should also continuously be rechecked. We also looked into something like an industry forum, an interest group. There was a discussion at the end that could help to around immersive media. I don't believe we have come to a conclusion, but some people in the discussion at least said would be an interesting idea to understand how we continue more consistent collaboration across the members in these different domains. That is about day one. I wanted to check if anybody like Neil or Brent, who were instrumental, or Imad, want to add anything on day one.
Hey, Thomas, no, I think that was a good summary. Thank you for, again, for organizing this event. I found it useful. I hope others did too. Appreciate everyone making the time to attend. I thought it was a good update on the related work that both organizations are doing, good update on status and milestones. And I too hope it can be a good starting point for continued coordination between the two groups. So thank you.
Thank you.
I can't add anything to that. I mean, that's perfect. And you'll say it all.
Thank you, colleagues. And again, we have some room, hopefully some room at the end of the day for discussion. But I would suggest we look at the program for today and starting into the second session. For today, we basically have two sessions. One is video and 3DG. So basically, we have presentations from the MPEG 3DG and video group, and thank you to Marius and Vlad for preparing this, giving an overview of what's happening there. And then we also have a more specific aspect that relates a bit to the discussion we had yesterday, a video decoding interface, and how it relates to OpenMux and Vulkan. So Emmanuel is going to present this. And then from a Khronos perspective, what's happening in the Vulkan group on video extension, Ahmed from the Khronos group is going to present this. The second part of the day is going to be more related to XR and systems, and we have a couple of aspects in MPEG-I that relate to more system aspects. So first of all, phase 2, haptics and audio. So we're going to have shorter presentations, just give an overview on this one. Thank you to the colleagues from MPEG here. And then an introduction to Khronos OpenXR and what's happening in 3GPP. We're also going to have a bit of a discussion room in between. I'm going to announce this ahead of time. I hope there's a couple of minutes at the end to wrap up and identify some next steps, but we're surely going to be closing in 2 hours and 50 minutes. I will not introduce the speakers in details. So if you want to know more about the speakers, they're all LinkedIn links provided, so you can read a bit on what they're doing today, or also about their background and history. Having said all of this, I still wanted to check if there is any questions before we start with the presentations, and then I would hand over to Marius or Vlad, checking then who is going to be the presenter. But any questions? And please use hand raising tool preferably, that would be great. No? Okay, in time for Marius. Marius, I stop sharing and then you should be able to share. Let's go ahead.
Good. Thank you, Thomas. Hello, everybody. Let me share the screen first. Normally, you should see the slides, and then if I do it small, yeah.
We can see.
Good.
Go ahead,
you can hear. Good. Hello, everybody. So let me spend some minutes to give some updates on what we are doing in 3D graphics coding. But I know some of you already know my slides because I use some of these slides to present the activity in the group. But even for you, I have new slides. So don't go away for the coffee now, stay and listen. But we have many other people that don't know or know very few about 3D graphics coding group. And I would also like to use this opportunity to introduce who we are and what we are doing. So the topics of today are three: few minutes in describing what the group is and trying to to also give some hints why the group exists. Then a short review of what we did in the past, and I will spend much more time to describe what we are doing now, because I suppose it is much more interesting than the past. Okay, so mainly MPEG 3D graphics coding is an ISO working group. We are part of MPEG. For years, we were under the umbrella of the MPEG working group as a subgroup, but now is an working group like any other working group in ISO. But what is more important is that the group aims to develop standards for graphic compression. And I put in red compression because this is the keyword. Mainly it is application agnostic. It covers a variety of data representation models. We know that in the 3D graphics world, this is one of the issues. And it applies, at least up to now, traditional signal processing, like that the ones you retrieve in image coding, in video coding, in audio coding, or what other any other kind of signal, which are the components like prediction, frequency transformation, quantization, entropy coding, and more or less that's all. We start some activity on a new kind of coding because it's very fashionable today to do machine learning, and we are still trying to see if there is any benefit. Probably there will be some benefit in the future to look for some data-driven models and not the ones that are usually used. But anyway, in our discussion of today, I will talk about this traditional signal processing coding. Okay, why it exists? Mainly because, like any other media, also 2D, but 3D graphics needs to be efficiently stored and transmitted. We may wonder if this is a need, and especially in the past, the need was not so strong to have advanced models for compression. But now, nowadays, more and more we have this need that is more present. However, it's not as easy. Even I don't want to minimize the work of other groups, but it's not as easy as, let's say, image or video, because the graphics relies on mathematical models, which by definition they are compact. So if you, on top of that, you want to add compression, of course you can compress, but it doesn't, since it's a model, it's not a signal, doesn't have the same properties as a signal. So the question may be, should we compress the model or should we compress the result of model interpretation? There are different levels where the compression can be applied. And this comes with additional difficulties, like the variety of the model. We know that for different applications, we have different requirements and therefore different representation models. So we are mainly talking about meshes with triangles, but in 3D graphics world, we have much more than that. So any variety that we add in the system has deep implication in how the compression is done. But also 3D graphics is not one media, but is a collection of media. We're talking about geometry, material, animation, and many other signals that are used in graphics application to do the render. So even if conceptually compression is reducing the size of the data for efficient storage and transmission, when we apply this simple concept in the world of 3D graphics, the difficulties are much more different than what we are doing usually with a simple signal. Okay, what we did in the past, actually the activity on compression start in the last century, even last millennium. For some of us in the call, we were there. I hope there are also young people that don't know about all this history, but it's nice to remember what we did in the past and how we did to to have some learning from that. So you may know MPEG-1 was published in 92, 94, and was of course only audio and video. But in 97, VRML was published. Yeah, for the ones who don't know, this is a 3D format at that moment intended for the web. Okay, and what MPEG did in one year after is was to ensure that VRML can be compressed and streamed, which, if we have in mind that this was the last millennium, was quite ambitious. So there is something in MPEG-4 called BIFs that is doing binarization of VRML, extension for streaming, extension for server commands, extension for 2D graphics. So listening and knowing what we discussed about glTF, this reminded me that few years ago, MPEG did the same for VRML. I hope it will be much more successful for glTF than for VRML. But in the same time, we realized that there are some, I continue to call signals, but it's about content. It's not a signal in the sense that was captured by the reality. But we realized that there are some signals, some content that can be compressed in a particular manner, because we can find correlation in that signal, therefore do the compression. And in 98 was about the mesh. 3D correlation in mesh can be used to do compression, and face animation, mainly because there was a parametrization of the face, and the displacement of some key points can be followed in time and have temporal prediction. So there is something in MPEG-4 called mesh compression, back 98, quite old, and face animation. And 1 year later, we did that for the entire body animation. And we had, so 1999, that is a demonstration that was done at that time of augmented broadcasting. So when we are hearing now about new application in terms of augmented reality, actually they are not so new, because people made that even in the past. Here are some illustrations about progressive mesh coding. So all this stuff that looks fancy today, they are there, and they were quite known. So we continue, and starting with years 2000, we include new set of data to be encoded in terms of geometry, appearance, animation, including the compression of skin models, animated skin models. Then we had morphing, we had multi-texturing, we had a model for terrain that was very, in the years 2005, 2007 was very, let's say, hot topic to have large terrain navigation, and therefore to have streaming and compression of all that. In 2001, we also had something that we called scalable complexity mesh coding that includes DFAN, which may be a tool that you have already heard about. So these are codec tools, compression tools. But something interesting is that at different times, we also try to apply the compression to data models formats that were defined outside the group. And in 2004, we create a profile with X3D from Web3D Consortium that was common. So X3D is only for raw data, and we add compression on top of that, and we create a common profiles. And in 2009, we also create another part, where part 25 is known as part 25 in MPEG-4, that is allowing compression of third-party XML. And here you will find Collada, that many of you know very well. So if you want to have Collada compressed with MPEG, now there is a standard to do that. Okay. And this trend of more efficient compression was continued with different types of content, meshes with multiple attributes, multi-resolution mesh coding, and even a form of that we call 3D graphics coding for browser, when the decoder is getting JSON that you can directly display in WebGL. So if I put all these tools in one slide, we will end up with a very rich set of tools covering what is, let's say, most known in graphics world, from index faces, triangle surfaces, patches, subdivision surfaces, waveless subdivision surfaces, mesh grid, solid, even we have compression for solids, TFAN I mentioned, and also going from shapes to textures, different kind of representing textures and animation. Like I mentioned before, the interpolators, very well known, and the skinning model, also of FAMC, that is presuming that presumes the animation is obtained by skinning, but is not coding the skinning model, but the result, and also morphing. So my point here is that in terms of compression technology, we have a lot of compression technology that that can be used. Some of them are still state of the art. Of course, even the compression knowledge was improved in the last years. So maybe some tools can be considered as outdated, but the core is there. Okay, so after all this history of what we did, the point is what we are doing now, and we decide to not quite recently, a few years ago, to focus on application where compression is really needed, in the sense that many graphics applications are doing light compression. Light is like zip compression, and it may be good enough. If you only have to reduce the storage, or you transmit the data as a single packet, then you just zip, and it will save some bandwidth, and it may be good enough. So the question is, what zip cannot do, or is not doing good enough? And one of the use cases when this happens is what we can call realistic graphics, or even better is graphic representation of the reality, because not every time the content looks realistic, but the idea is to not compress the content that is usual content in 3D graphics application done by modeling software, but to capture the reality and represent that reality. Okay, so since we are discussing about this use case of capturing the reality, what usually we are doing, we started years ago with capturing an image, capturing two images, for the stereoscopy, capturing larger and larger images with deeper and deeper colors, and with many and many cameras. Okay, so one of the questions would be, what is the most appropriate representation form for this capture of the reality? And we have several: video plus depth, where we have several videos plus depth, or we have point clouds, and we may also have a mesh approximation of that reality. Some other groups in MPEG are working on encoding video plus depth with the same idea of synthesizing new views from what is in the bitstream. And what we worked in the last years is on point cloud, and what we will do in the future is this new dynamic mesh. Okay, but let's move on. That made us focus on the point cloud compression as a representation of this capture of the reality, with several advantages. That point clouds are easy to produce. Of course, you have to have the material, but in terms of producing high quality content is much easier than using authoring tools and try to create realistic content. And since is model-based representation, it gives you for free the interactivity and the immersiveness, because you still need to interpret that in the rendering engine and produce the pixels. Okay, I will not go in all the details what the point cloud is. I think everybody knows, but mainly is positioning space on top of which we add different properties. Some illustrations of that. Here is a point cloud. Of course, we can visualize it as a video in a PowerPoint, but is a point cloud, a reconstructed point cloud from different views made by 8i some few years ago. Some others that you may know because they are widely distributed, one from Intel, another one from Microsoft, where we see this kind of new use cases where we can turn around the object because we have the object as a 3D representation, or with the AR glasses here, we can watch these small objects, which are point clouds, because they were obtained by reality capture. Another example here illustrating the same similar concept. We have a real person, another real person wearing the glasses, and what this guy is seeing, it's of course he sees the real person and also a virtual one that was captured in another place and transmitted here and visualized in the glasses. Okay, but point clouds are not only used for this kind of use cases, but also for what is called assisted driving or autonomous driving, which the impact in terms of our life will be even bigger than other kinds of point clouds, because many of our cars today and in the next future will have this kind of representation to assist us or even to take our driving place. Okay, so if we deal with this kind of content, one of the characteristics is that is huge. So here, just to simplify, this content has 800,000 points, approximately in uncompressed domain, 1 gigabit per second. Okay, just to have in mind some numbers. Some basic principles in terms of compression and why is not as easy as in 2D space to do compression of point clouds is usually we are looking for correlation. So we are trying to predict the current information with respect to what was already transmitted. Even in 2D, we have 8 neighbors and all of them can be used as predictors. But in 3D, we have 26 and many of them are transparent. So we have somehow to drive the way how the predictor will be chosen. Of course, compression in point clouds is not new. There is a lot of academic work on that, and even not only academic, but even some products. So what people are usually doing are creating some constructs that will change the space, the representation space, into another space in which predictions are easier to find. And 2 examples, OP3 and KD3, I will not go in detail, but is a manner of segmenting the 3D space in subspaces and follow the hierarchy of subspaces by following the shape of the object. Okay. They are great for static scene in terms of compression, I mean, but they're not so nice for dynamic content in the sense that, imagine this case here, we have the OP3 that is created by subsampling the volume in small cubes, and then if the information exists in one of the subcube, we'll continue the division and we create this hierarchical tree. So, but what is happening is that during the animation, the motion, it may happen that this guy will jump not in the neighborhood on the right side, but on the left side. It means that the entire tree will be reconstructed, or a large part of the trees will be reconstructed. So it will be cut somewhere here and reconstructed from this place. It means that what we targeted to have a nice prediction space was destroyed. So we have to pay attention when we deal with dynamic content and using this kind of constructs. Okay, we observed that this point cloud trend is something that was growing. We started the work in 2014 in MPEG, in applying compression on this representation. So we had a call for proposal, usual stuff, and we end up, that is important here, with two solutions or two families of solutions. Let's say two standards. One is called video-based point cloud compression, and another one is called geometry-based point cloud compression. And I will try to give you insights why we have to. Okay, both of them are already standards, and VPCC was recently published by ISO, and GPCC is in the process of being published, but is finalized. Okay, what is video-based point cloud compression? Actually, we reused some of the basic ideas from graphics community, and one of that is to use the concept of the displacement mapping. So in computer graphics, we have the texture and we use the texture to create the geometry, like a displacement mapping. Here we are doing the other way around. We are trying to to project the geometry on a plane and only keep the distance with respect to that projection plane. And another idea was what we are usually doing in texture mapping, when the color of a vertex is taken from a texture, and we just encode the position of the pixel that corresponds to the vertex. How it is done in the case of point cloud? So imagine you have the point cloud, you have a projection plane, and then we project all the points on that projection plane, and we encode the distance with respect to the projection plane. The problem, if we are only using a projection plane, is that several 3D points will project in the same plane. So somehow we have to use more than one projection plane. And the way how it is done is what we call patches. So the object is cut in sub-objects, and each sub-object will be projected on one plane. So the standard doesn't mention how these sub-objects are created, and we expect a lot of competition to be there in terms of compression performances on the selection. Of course, the reference software includes one way to do that. And then once we have the patch, a plane will be selected, the most favorable orientation of that patch, and the projection will be done. There are a limited number of projection planes, the 6 orientations of the cube, plus the planes which are rotated by 45 degrees. We only select this subset of planes because it allows to have all the operations in integer domain. Okay, so it means what? Our 3D object, which is a point set, is replaced by a set of images, an image coding the geometry as a distance. So this is a grayscale image, and the other that is encoding the color of that pixel. Okay. You may notice that some pixels in the images are not used. And to inform the decoder which pixels are used and which are not, we also encode an occupancy map. That is a binary mask saying 1 or 0 if the pixel is occupied. Still, by having these 3 maps to the images, it still may happen that some 3D points will be projected exactly in the same 2D pixel, in the same position of the pixel. So it means that we have more than one pixel in that position. And to avoid that, or to compensate that effect, we may encode several depth maps corresponding to different pixels. You may notice that still we have an approximation. It's not a bijectivity between the two, because there are some pixels which are missed by this projection, or we should have many depth maps to cover all these cases. And to avoid that, we have a particular patch that is called a row patch, encoding directly the position, XYZ position in the image. In general, they are very small, but that is to ensure that we have the lossless coding in the case that application requires lossless coding. Okay, so the summary of that is our 3D object now is replaced by this set of maps, 2D maps. And since MPEG is very good in video coding, that will go in classical video codecs, and the problem is solved. I put an almost because in general, the video codecs would like images that are much more continuous than that. So there are a lot of ways to ensure that the images that are obtained here by projection of the patches are much more fluid. But as I mentioned, this is something that goes beyond of the standard, and people will can do competition there to have better methods of packing, of patching, and therefore have a real impact on the compression performances. Few numbers to summarize this part of video-based point cloud compression. You remember our objects that was about 1 and 3 gigabits per second. When we compress, these are objects like humans, let's say, with human kind of motion, human kind of texturing and colors, and that acceptable quality, we have numbers like this one, 4, let's say 5 megabits per second, 7, of course. If you want to have better quality because you have larger screens, then you have to go higher. But it still is comparable with other kind of media that we are transferring today. A few words about software is available for encoder and decoder. There are also implementations on Android available, even Windows phones, Windows, Mac. So you have all the references on this website. Good. Yeah, that shows how we progress from meeting to meeting in terms of compression performances. I will not go in the details here, but I can make available some slides with the results in terms of compression. I will spend a few minutes, not too many, because I don't have too many, speaking about geometry-based point compression. And maybe you noticed that the video-based point cloud compression works well when the content is dense enough. But in the case of autonomous driving or assisted driving, the point clouds are sparse. So if someone tries to project that and encode images or videos, it will not be as performant as a dense point cloud. So therefore, the idea here is to exploit directly the 3D correlation and encode them as such in 3D. Since one of the use case was assisted driving or autonomous driving, we want to have lossless compression for this particular application. So yeah, before giving you the numbers, just to show how it works, I will not go in details because there are many, but it uses a set of geometry tools like optic coding, triangle soup, direct predictive coding in the 3D space, and some transforms for the attribute coding, like an LOD scheme and the RAT. If you need more details on how it works, you have the material available on the web. But in terms of performances in lossless mode, for this kind of content, of course, it depends on the complexity of the content, we may have up to 25 megabits per second. This is the list of tools, not going in details. The point here is that depending what kind of content is to be encoded, we have to use different tools. But all of them are in the codec and specified by specific profiles. Okay. In a few words, what's next? Next is back in the past, in the sense that point cloud may be a nice representation, but we know that it is very costly in terms of rendering. So there are some works trying to approximate the point clouds, the one that are captured from real life with meshes, and we are now working on compressing this new kind of mesh. It's a new kind of mesh because with the as a difference with the traditional meshes, they are still a set of 3D points, but their connectivity is varying in time. So we don't have the same connectivity as for the classical animated meshes. So what we have to encode, of course, XYZ, that is going in time, but also the indices, the vertices that are changing. The texture is not a texture anymore, but is a video. The texture coordinates are also dynamic. So we have much more data that is dynamic. And what we are looking for now is, we are developing a standard for encoding that, but using the same approach as VPCC. And this approach is using the projections. We use the projection for encoding the geometry, the attributes, and we will add something for the connectivity that can be TFAN based because it's a tool that exists, or something else that people will come with. So this is an exploration still in MPEG. We have the call for proposal to be issued in October, and the technologies are expected to be submitted in April 2022. Okay, my last slide is about 3DG and Khronos. I tried to somehow imagine what we can do together. We had several discussions in the past. I met Neil several times, and I think we know what other group is doing, more or less. But up to now, we don't have a concrete modus operandi. There will be already a good step forward that glTF 2.0 will become an ISO standard. It means that it will be like any other ISO standard, and we can build on top of it. One important thing is that MPEG 3DG is not developing standards for graphic formats. It's for sure not something that we want to do. And our dream is to have already these standards were deployed. But what we do is to add compression on these existing formats. Okay, so yeah, as I mentioned yesterday, maybe the way to do in terms of Khronos is to use the vendor extension mechanism of glTF. Of course, in terms of ISO, it will be a standard that we refer to another standard. That is something that we do usually. There is no big problem there. The point is that we have to somehow find a way that makes this development consistent in terms of what Khronos is intending to do, what MPEG companies are intending to do, of course, to keep the communication at a high level, informing each other, but maybe one day even have common roadmap or two roadmaps, not necessarily the same roadmap, but two aligned roadmaps. Okay, so conclusion of all these, point cloud is a representation that becomes interesting in terms of usability, because even if it's quite well known, point sets are there for years now. The real problem was the size of the content. So by compressing with VPCC and GPCC, we reach manageable bit rates that can be used in the application. One advantage of using VPCC is the fact that the entire VDOA ecosystem is there. So the hardware decoders are there, the transmission ecosystem is there. So VPCC is a set of videos plus some metadata. So it's very easy to deploy. If you have already deployed a video solution by design with no cost, no extra cost, you have a VPCC solution. And more than that, what we call V3C now is a solid framework that allows for compression of point cloud. Our colleagues from video are using the same framework for something that they call MIV, and we will use the same for mesh coding. I think that I used more than my allocated time, so I will stop here. And thank you.
Marius, thank you. Yes, we are a bit like at the edge, but I still would want to check. There's a couple of discussions on the chat, so I encourage here. But if there are questions, let's pick those up quickly before we move to the next one. But we have also a discussion session afterwards that we can use. So let me get my. I don't see any questions right now. So maybe we defer discussions when we have looked at all the 3 video topics and have a bit of an overarching approach and discussion. Yeah. How about that one?
Great.
Okay, good. So thank you again, Marius. The slides will be available.
Yep.
And I would directly hand over to Emmanuel then, but stay tuned for the discussion afterwards, Marius. Thank you. Yep. Emmanuel, should you talk? We cannot hear you.
Yes, that is better now. Thanks, Thomas.
Yeah.
Hi, everybody. My name is Emmanuel Thomas from Xiaomi. I would like to talk to you about the VDI standard today. And that's one of the many standards in the galaxy of MPEG standards. This one is run by the MPEG system working group. So there's a strong focus on interfaces between application, hardware platforms, and bitstreams. So to give you an idea of the reason why and the motivation of the work in the VDI and what we try to solve, I'd like to briefly go back a bit in time and looking at the MPEG 4 system decoder model, look at the extra applications that we were working with and that was raising some concerning issues for system integration. And of course, having some word about our ambition to specify extension for OpenMax and Vulkan video extension. So as I said, going back a bit in time, 20 years ago, roughly, this was the foundation for every, let's say, streaming application, over-the-top streaming application. That was the design that drives the application model. So on one hand, we have a media source, bitstream. It doesn't really matter how it was transmitted, whether it multiplex or not. The bottom line is that those different streams, the video stream, audio streams, can be separated, be fed to a buffer, and that buffer was used to feed a decoder. So you have one decoder per video streams. What is very important here is that by doing so, the MPEG-4 system specification introduced the concept of the elementary stream and the intermediate stream interface. These elementary streams are made of access unit, as we call it in MPEG, which are the smallest units of a stream with a timing property. So they go all in the decoder, and outside of the decoder, what the application gets is what we call a composition unit in this model. And composition unit are very simply put, if it's a video stream, a composition unit would be a decoded frame with a timestamp, so that at the end, for the presentation, then there's the compositor, as we call it, that can present them in a synchronous manner, because it's very important, as you know, that audio and video are synchronized. But it could also be the case for two video streams, for instance, be synchronized at the presentation stage. So this has driven 20 years of innovation in industry. This is still successful, but we've noticed that there are some limitations for extra applications. So to get a bit more concrete, we'd like to go through 3 applications. And I didn't know exactly the content of the presentation when preparing this, but this is great because they were all covered in previous talks. The VR tie streaming yesterday by Rakunen, and we got a lot of insight from Marius Preda just before on video point cloud and 3D scenes, basically. So going one by one for VR tie streaming, if you remember, or you can also check the slides that are going to be made available. In this application, there's two important aspects regarding the video decoding management. The application is requesting different bits of encoded video, and the requirement is to use only one single decoder that will be decoding those tiles. For VPCC, so you've just seen this is fresh, this is great. It is composed of several, let's say, sub-bit stream, as I would simply put it, which means that you would have, which means you would have one decoder for this sub-bit stream, and after decoding, they will be recombined to reconstruct the point cloud before display. So they are not meant to be presented as is, obviously. And finally, a 3D scene with a lot of objects. Maybe one day we have a bit more social workshop, for instance, in this kind of settings where we can see each other in a more natural manner. This is from a movie, by the way, but imagine if that application would require one video coder per object, or even more if the objects are VPCC. There are clearly a bottleneck for the device. Starting 8 or 10 decoders simultaneously is a very challenging task. So for those applications, that would be desirable to have a decoupling basically between the number of video streams you would like to decode and the number of decoder you have to start, so that there is a lower requirement on that front. So this is the applications we are mostly working on. But what does that mean exactly? Looking at the architecture I showed before. So let's take the example of VPCC. So the first question from the application perspective is, okay, I'm downloading that content, how many decoder I need? So very simply put, right now, the application was like, I'm getting that video, the VPCC bitstream, I will need one decoder per component, one for the texture, the depth map, and so on, as Mario just explained. But then comes here the trouble. So I'm running on a device, and there was this demonstrator from shown earlier, and we had a lot of interesting discussion actually at that point in time in MPEG. What is very well established today is that an application can determine beforehand the decoding capability for one bitstream. So you can ask the device, hey, do you support that resolution, that profile tier level, as we call it, on the device? It will say yes or no, even before the application can run, you can know that. But you don't know how many you can do in parallel most of the time. So what the application has to do most of the time today is to try and just asking at runtime, can I start this decoder? And you will get a yes or no answer. So this is very practical and pragmatic, but this does not really, let's say, ensure stability and a lot of, let's say, a nice ecosystem for implementers, because if you have to figure out whether you can display content at runtime, this is not very, very nice. What comes after, as we saw, is the decoders. So on that front, there is nothing really problematic. Assuming you can run those decoders, those encoded bitstream will be fed to the decoder. But here comes again a bit the struggle with this architecture from 20 years ago back. Is again, these textures and depth map, they're not meant to be presented together. This is not the point. There is definitely an extra step post decoding, usually running on GPU, in order to transform the decoded data back to something else that will be presented. And here again, we are looking at this architecture, we are lacking of something here to put the GPU in place. What is quite also specific is that traditionally we had a time-based synchronization. Here at the input of the GPU, you not necessarily talk about time-based synchronization, but more frame-based synchronization or frame-based alignment, in the sense that even the slightest shift from a couple of frames, they could actually create artifact in your reconstruction. That's actually something we got as feedback from early implementers of VPCC. So this creates some changes. To summarize those changes, the first one is the lack of interoperability for a group of bitstreams. This is very well known to do interoperability on one bitstream, but on multiple of those, this is highly tricky right now on devices. There is also a need to decouple the number of video decoders and the video bitstream you want to decode. Currently and traditionally, it was a one-to-one relationship. And this is quite challenging, as we saw, for scalability and higher or richer application like XR video call. And the last one is this new type of synchronization, post-decoding that is not time-based, but more frame-based, especially for GPU processing. So those three are the main challenges we derive from our study of these applications in comparison to the traditional MPEG-4 system decoder model. So now going to VDI, what does it bring to us? I'm going to show you now the architecture we have in VDI, and starting from what doesn't change. So what doesn't change is this. We still have decoders. We have an elementary stream interface in front of the decoders. And what is important to understand is that VDI does not intend to change decoders. So they are completely out of scope at this point in time. But what we care about is the interface around that. So we have the traditional elementary stream interface. The first important function we add is this input formatting function, which essentially is the mechanism to decouple the number of incoming bit streams and the number of decoders you need to run. So this function is, for instance, able to, from a media stream, incoming media stream, to create two elementary streams, or the other way around, it could take two media streams and merge into one elementary streams. Effectively, we then create this new interface, which is the media stream interface. And it sounds like a bit maybe black magic right now, what I'm saying. But of course, this is only working under certain constraints of encodings and specificities of codecs. So all of this is specified in the VDI specifications so that implementer will be able to leverage those functionality. On the other hand, we have the similar function, which is the output formatting function with the same idea here. If you have two decoders running, why would you not have one buffer? Because that might be easier for application, or the other way around. If you are, let's say, stuffing different components into the same video frame, you may want to actually access them via different buffers. So there is also this function there. And very importantly, we can also from the VDI specification, this aspect of grouping decoders, so that the output is in a synchronized executed in a synchronous fashion. Because again, from the application perspective, you take the VPCC example. There is no use of having many frames in advance for the texture while you're lagging behind for the geometry, for instance. You want to have those in a synchronized manner. So that GPU processing can happen in the best way possible on the right side. And of course, all of this is wrapped up. So this is what we call the video decoding engine, which is a concept we map, at least from our perspective, onto existing APIs, and OpenMax and the Vulkan Video API, for instance, are the two APIs we are working with in VDI. And what it allows us to do is also extending the querying configuration capability so that the application can have some guarantee beforehand or at runtime optimize the operation of the application. So there's a lot of coordination to be made there. So to sum up, what VDI brings on the table is, first of all, interoperability point for a group of decoding instances running simultaneously. This is highly unpredictable right now, looking at devices out there. Secondly, there's decoupling effectively implemented by bitstream merging and rewriting functions. Important to know also that obviously those are codec specific. You cannot define that in an absolute way. And currently VDI draft is providing those functions for the HEVC, PVC, and EVC codecs. We are mostly working on MPEG-based codec. However, there is no reason why those same concept could not also be applied to other codecs, say AV1 or any other video codecs. And finally, something that VDI tries to improve is at the moment you start simultaneous decoders on the device, we do not want to have competing decoders. We want to have a collaborative way so that the application can run in a more stable manner. Maybe you avoid some buffering because of this competition, and ultimately improve also energy consumptions on devices. Now going a bit more into the grid details and the extensions of OpenMax and Vulkan. OpenMax we started with 2 years ago roughly, so it is more mature than the Vulkan one. In a nutshell, what we have is a set of functions that are new to the C API of OpenMax. Oh yeah, I need to also clarify that we're talking about the integration layer, and sometimes we forget about that. From the VDI perspective, that's the specification we are interested in. So we are introducing new set of functions for the query capabilities, for this grouping of decoder instances. And also quite interestingly, we have a reference software that we based on a GStreamer OpenMax implementation that we found out there. So we're continuing this to be aligned, and that would be a deliverable of VDI next year. On the Vulkan video side, so this is very early for us. We just have one meeting cycle of work on that. However, we do have initial mapping at this point, and I'm sure that will be much clearer after the next talk. But there is a concept of Vulkan video session that we intend to map currently on what we call a video decoder in our specification. We found that extending the video session in Vulkan to accommodate multiple decoder sessions was too much of a stretch. So we decided to go with a kind of a wrapping approach there. We also have the question about how do we extend the Vulkan video API, whether we more or less start from a unique point of extension or we extend many objects. We went with the first one, which is that we have standalone objects with parameters that maybe overlap with other parameters, but for the sake of simplicity so far, that's what we started with. And this is very early. We're still in working phase. So we hope that we can get also feedback during this workshop and after to make sure this is the best approach possible. Currently, we don't have a reference software, but this is the ambition of this work as well, to provide us with software implementation so that those specifications are not only paperwork, but also implementable in the industry. So this concludes my talk. So why we did that is, yeah, we noticed some limitation of the traditional model that was running for 20 years. And that made a lot of burden for application developers. Yeah, we are seeing even richer application, XR space, and there's a lot of limitation on the device. By the way, some of these limitations sometimes are solved by network capacities that can be complementary. I don't think there is a winning solution, a winner-take-all solution here. The way to do that is that MPEG VDI will develop functions for a manipulation of video bit streams to decouple decoder instance and input bit streams. And we also have extension for, as I said earlier, OpenMax and Vulkan video extension. In terms of timeline, we intend to finish it by next year. So the specification will come with reference libraries implementing those bitstream manipulation functions for the codecs, as well as the documented extensions for Vulkan and OpenMax. And that concludes my talk. Thanks a lot.
Emmanuel, thank you very much. So let me check if we have a couple of comments or questions, but again, we are running a bit short in time, so I wanted to check, just there's some good discussion also on chat again. Marius is picking up some aspects. Some immediate questions to Emmanuel. Maybe again, we can bring it into context when we come back and we look into the Vulkan video extensions now from Ahmed, and then we come back. So Emmanuel, please stay available and then we bring it together.
Sure.
Ahmed, would you be able to share your screen as well?
Yes, can everybody hear me?
Yes, perfect, thank you.
Great, so let me share. Can everybody see the presentation?
Yes, thank you.
Perfect, thank you very much, everyone. And this is gonna be a very brief introduction actually to Vulkan Video, the work being done by the Vulkan Video TSG at Khronos. And basically, the intention is to provide you the high-level background you need to start reading more about Vulkan Video details through the blog or the spec, and then we can think of how things can work together between this new ideas from MPEG and what we're doing for Vulkan Video. So why Vulkan Video? So as we all know, Vulkan is very popular for many use cases for graphics and compute. And however, it has a gap for video. Basically, it doesn't have any video support. So if any use case wants to use video decode or encode, it has to interop to another API that exposes this hardware. And basically, it could be a different API for different platforms and so forth, right? So the main goal of Vulkan Video extensions that we're working on is to define these video extensions natively in Vulkan so it can be tightly integrated with the existing functionality for graphics and compute and display. So in doing so, we leverage all the cool and advanced features that the Vulkan framework provides for scheduling, synchronization, memory utilization, all this low-level control that people love about Vulkan, right? We are leveraging that for video use cases now by adding these extensions. So basically, we should be able to see a new way of using video hardware and new improvements to video hardware to make more use of this low-level control for Vulkan. That's the hope of having these video extensions. How this is done at a very high level is by introducing two new command queues, one for video decode and one for video encode. And in keeping with the Vulkan philosophy, we're trying to make the interfaces for video decode and encode to be low level and provide as much flexibility and control to the application as we can, given what we are working with from the implementation support point of view. So we expect Vulkan Video not to be useful just for the standard PC use cases, but also for embedded use cases with more constrained, power or memory, as well as the high performance server use case. So at the high level, what are the stages in a typical Vulkan Video application for decoder encode? If you're familiar with the video pipeline, then this is going to be straightforward, right? We rely on basically standard Vulkan objects to represent memory resources for bit streams, buffers for images that are input or output, or reference images is the PK images, right? So the application will use the standard Vulkan interfaces to allocate those resources. We introduce, as you learned from the previous slide, previous presentation, a new object to represent the video session. So as Emmanuel mentioned, if you want to work on multiple streams, video streams in parallel, you create one video session per stream, and that would represent the stream that you're working on. Although you could reuse the stream, the session for more streams later on, right? We also define what we call session parameters objects. So with video codecs, often there are various sets of parameter sets that are reused across many video frames. So like sequence parameters or picture parameters. And to avoid reprocessing these parameters over and over when decoding or encoding many frames, these objects are created to do this processing once for every new set of parameter sets, and basically reuse that processing or leverage that processing over many frames. Right? So this is great for efficiency in this new interface. And finally, the main other thing is basically for the application to record command buffers that perform the video operations and submit them with the required synchronization. We'll go through a bit more detail in the next slides to sort of see how this works, right? So basically for the video decode process, you're starting with an input file that's a container with an elementary bit stream, or you're maybe streaming this, right? And the application, as with other APIs, would handle the demuxing and parsing, right? And once it figures out at the high level, what's the video profile it's working with, what are the memory requirements, but it's able to create the video session for the stream, right? And as it parses different access units or NAL units that it receives from the bit stream, the elementary bit stream which we work on, it's able to determine, okay, I have a new sequence parameter set, a new picture parameter set, and so forth, and create the appropriate session parameters objects or update existing ones, as well as populate buffers with bit streams that will be submitted decoding later, right? So once this information is known, and the application is also managing what images are going to be used for decode output or reference and so forth, the application is able to record command buffers to perform the video operations. So there is a new API to introduced by the video extensions to record video decode commands to the command buffers. And as with other Vulkan command buffers, this recording can be done in parallel, right? And then submitted in decode order, the decode queue, or rely on timeline semaphores to do the proper ordering at the execution time. So all this is now making use of the standard Vulkan framework for synchronization, right? And once the commands are executed, you're also relying on the standard Vulkan framework for determining when the job is done and when you can access the output images. And then finally, any post-processing is done externally to the Vulkan video extensions themselves. So this is a brief walk for decode, and we have something similar for encode, except as usual with other APIs, encode, the application normally has to do a lot more than decode, right? It has a lot more decisions to make. And in Vulkan video, this is, I would say, into the next level, right? So in Vulkan video for encode, the application is not only deciding, high-level settings like rate control and maybe the picture type or something like that, but it's also deciding how to do the reference management and even how to determine the syntax in the slice headers, for example, related to the reference management, right? So the implementation is receiving all the syntax through the interface, which is and it's only coding the slice header. All the decisions are being made externally by the application. So this is sort of a new type of low-level control for applications that we hope will enable more optimizations that are use case specific. For video encode, the same objects apply, the video session parameters, and they're used, the same as decode, right, except in the reverse order. There's a new command to record encoding operations, as well as a new command which we call control video to configure the stream for execution time behavior. And this is used primarily right now for rate control configuration. So if you want to configure rate control or just rate control for the video stream, you'd use this command, and when this is submitted or executed in the execution timeline is going to impact the rate control algorithms that a lot of implementations support today. Also, Vulkan has standard commands for query operations. So those are leveraged for video encode in order to determine or allow the implementation to report the bitstream sizes that it's going to generate for each frame. And the standard API is used to retrieve those results by the application, right? And then finally, any muxing or anything else happening afterwards is done by the application or SDK. So shouldn't be surprising, right? Basically, what you'd expect, we hope, from an interface for Vulkan video. In terms of how the extensions are defined, as you probably noticed from the previous slides, a lot of the objects are common between decode and encode, and even codec independent. So these are defined in a core video extension, which is VKKHR video queue. Most of the APIs for Vulkan Video are actually defined in this extension, just for managing the sessions or session parameters, querying capabilities or supported image formats, the stream control command. We also have commands to sort of set up a command buffer context for video, which is helpful if you are going to perform multiple video operations in between the begin and end commands. And you cannot use this extension by itself, right? You have to, if you're doing decode, you have to use also a core decode extension, which is decode specific but codec independent. This extension primarily adds the command to record decode operations into the command buffer. And there's a similar core extension for encode that is a similar command for encode. And then we define a set of decode and encode codec specific extensions. For example, decode H264 and decode H265 and so forth, right? So basically, let's say an implementation only supports decode H265. It would need to expose the core video extension, the core decode extension, and the decode H265 extension, right? Right now, there are no API hooks defined in any of the codec specific extensions. They only define structures that are chained to core structures here to provide codec specific information. And the codec 65 extension is what we're working on today. And basically that's still coming soon in the provisional release for video. If you look at the provisional release for video, you'll see all these other extensions. This one is not pushed out yet. And as you can imagine, you know, other codec specific extensions will be added, you know, similar to these for H5, and we don't necessarily have to, you know, define or mirror the decode and encode part. So for example, we may not add the encode for VP9, for example, unless, you know, we have real interest and support for that. Another point related to how the extensions are defined is basically we didn't want the Vulkan specification to be, you know, sort of copy paste or, you know, superset of multiple codec specifications, right? There's a lot of details provided by the codec specifications that lives already in the codec specifications, and we don't want Vulkan spec to duplicate that. So to help with that, what we try to do is to split out anything defined by the codec specifications into separate headers, which we call codec standards headers. For example, we have a set of headers for H264 and a set for H265. And these headers would define types and structures that are codec specific. For example, you'd find here, you know, the sequence parameter set structure with all the SPS fields or syntax elements that exist there, right? And we even use the same naming convention for the codec for these fields, so that, you know, a video expert or someone used to video coding would just look at those fields. If they want more information, they just search the video spec and video codec spec and find the information about that. And the extensions here are more isolated from basically what would be documented in the codec specifications. So this is a, you know, a very brief overview. If you want more information, a good place to start is the provisional release blog, where we have a walkthrough of the standard use case like transcoding, and basically use that to provide more details about how the Vulkan API works. And then if you want all the details, the provisional spec for Vulkan Video has that. It's still a work in progress, and obviously, just like we want feedback from you know, Vulkan experts on how this is looking, we also want and really appreciate feedback from video experts, and can be provided in the GitHub issue for the provisional release. And then if you want, hands-on experimentation with Vulkan Video, NVIDIA has provided bed drivers and a sample app decode that you can get your hands on and play with, right? And we even have GStreamer providing also a sample app decode. I think Victor is also on the calls. So basically, looks like there is interest in basically already in adopting and using Vulkan Video, and we're happy to hear and learn how we can collaborate with MPEG in order to make the new use cases work as well. Thank you.
Yeah, Ahmed, thank you. Very interesting. I believe that is really at the heart of some discussion that should have. Going into the details might be a bit tricky, but and we're a bit short in time, but I still want to spend like 4 or 5 minutes of wrapping up the whole video discussion. So I'm opening up for comments and questions on all 3 talks and see if there is any observations, specific questions. Please raise hand. Emmanuel.
Could I suggest either Ahmed or perhaps Tony, okay, can you spend 30 seconds just summarizing, do you see a good fit between VDI and Vulkan Video?
Yes, I mean, when looking at Emmanuel's slides, how Emmanuel captured the elementary stream video decoding process as something that's, a separate block being used by VDI, that made me automatically think, okay, this fits very well with Vulkan Video, because we're only defining something that works on the elementary stream and handles video decoding itself, right? And then all this extra technology being added by VDI is sort of around that and use that as a building block and extends that. So even when Emmanuel mentioned how they would extend the video session to the Vulkan Video session that we're defining to do that, that made sense as well. So certainly it seems that at the high level, it looks like it can work, right? And we just need to get into the details to see, what's missing or how things will work overall once we have all the details.
I do second that, and I just wanted to add that all the control that VDI is asking for is already there. Not only when it comes to you could orchestrate all the different video streams you've got per frame, even per slice basis, perhaps in the future, but also synchronization between them, synchronization with graphics, cooperation with graphics. There's no fancy interrupt that you have to deal with in comparison with other APIs. It's all images and buffers, which are already Vulkan primitives. So, for example, in the decoder use cases, you decode images and you're in full control of these images are already in the GPU memory, and you could, for example, do 3D post-processing or additional data against it without any additional interrupt APIs and things like that. Then you could do queuing at the GPU side of, for example, decode frame from one session, and then 3D operations, one or multiple synchronized by synchronization primitives. And then another session could actually queue up work, and you could compose stuff on top of that without even going back to a CPU and doing stuff. It's all done at the GPU side with the command queues, which you could cooperate and synchronize between those primitives. So definitely a lot of control from perspective of DAP over the codecs, including you have full control over the reference images and how many you wanted to allocate, how do you want to use those reference images, full control over the hardware.
If I may just add a quick comment, and I think it's very interesting for further discussion then, if high level we align. I'm just wondering if you had a specific discussion on this question of coordination between simultaneous decoders running. What they are discussed already, yes or no, and if you had any early conclusion on that.
So I think you've correctly pointed out that a session for us is a decoder. We don't, so in Vulkan Video, you may have multiple decoder devices from hardware perspective, multiple instances, but a single decoding session is really represented by a video session. So when you are decoding a frame, you may create as many sessions you would like, and those are going to represent multiple elementary streams, may represent multiple elementary streams or anything else. And you may only use a single hardware instance in those cases. Or you may decide that you wanted to better utilize the resource of the system. And if you have multiple hardware encoders, you could do a combination between both. You could have multiple hardware encoders plus multiple sessions against those, and you could utilize, the hardware resources in a better way as well. So it's up to, again, full control to the ops to decide how those should be done.
Okay, thanks.
Sure.
Yes, thank you. I believe, I don't believe we can solve that now with a discussion. It's probably good to look at the presentations, look at the resources, and potentially, similar as we did with the glTF, come back to a follow-up discussion, maybe exchanging more information, looking at the extensions. VDI is at an earlier stage. We also need to check at what stage Vulkan Video is. And I think there's another question on the ubiquity of Vulkan Video. It's clearly one way to address it. We know that OpenMax is still an interface that is quite often supported and so on. So I believe having all of this information collected just helps to understand where we stand, and then hopefully people know each other now and we can reach out and have a follow-up on that one. That would be my conclusion on this video discussions now. But information sharing, I think, was great, and investigating more details and coming back to details might be needed. Let me check if there is other questions on that topic. No. Okay, I know that was a bit short in time. People exhausted their time for the talks, which is fine. But having the collection seems to be, and the connection seems to be the right way now moving forward. So I would like to close this video session then and move to the last session, the fourth session, which we call XR and systems. And as we said, there is a couple of developments in MPEG that we would like to introduce, and we allocated 12 minutes for each. So Imad would be first, then we would have Chris, and then we would have Skylar. Maybe the three could go directly, handing over, and then we have a brief discussion after those three introductions are done. Imad, would you go ahead and share what we've done in MPEG Scene Description Phase 2?
Yes, definitely. Let me share my screen. And this time it's in full screen mode, I hope. Can you see my slide? That's it, slide deck.
Yes, perfect.
Okay, very good. So good morning, everyone. So this is more like the part 2 of what we presented yesterday. It's actually what we call phase 2. It's a collection of features that we actually down prioritized, not because of their importance. I think they are very important, but more for the trying to address like the basic features in scene description first. So we did the timing aspect that was done in phase 1. Phase 2 will be looking at now my computer refuses to present. So first, well, I'm sorry for this. I need to start PowerPoint. And going full screen was not a very good idea after all.
You knew it yesterday. You want to hand over to Chris maybe first, and Chris does it first?
Yeah, probably this is.
Chris, would you be ready?
A few minutes.
Yes, I can go.
Good. So let's do it like this. So
Sorry
we
for
swap
that.
and start with the, and then we do Skylar next, and then we come back to Emmet. So MPEG haptics. Chris, thank you.
Great. You can see my screen, right?
Yes.
Awesome. So I'm going to talk briefly about MPEG haptics. This is a new media type that's being introduced into MPEG and definitely has overlap with a lot of immersive media experiences that we've been talking about the last day or two. It's currently in WG2 technical requirements, so it's still at the very sort of early stages in the MPEG process. But for this community, I wanted to give an overview of some of the use cases because it may be a new area for some of the community. But I mean, essentially, haptics has been around for 25 years or 30 years or so. And in immersive media, it's particularly relevant and generally has been pretty well used. More recently, some of the use cases that we see and that we're trying to articulate in an upcoming use case document that's going into MPEG 136, you see these kind of glove exoskeleton type interfaces here that provide some kind of resistive feedback to a user's fingers. These can be used to feel the shape of objects in a 3D immersive environment. So this is a popular, emerging popular use case, I would say. One that probably has been seen, I think this video has been watched, millions of times on YouTube, is this shadow robot demonstration where this user here has some fancy haptics gloves, DK2 gloves that they're wearing, and they can actually feel the same sensation as the fingertips at the end of this articulated robotic arm here. And so that allows them to solve a Rubik's Cube in a teleoperation context. A fairly common use case that we see actually is training and simulation. And this demonstration here shows a device which is a combination passive active haptic device that has an active trigger mechanism here. So when you pull on this trigger, you feel some kind of resistance that's programmably controlled. And there's also a recoil mechanism inside this device. But the shape of the gun configuration here actually also provides a haptic sensation to the user, which gives them some training value. Other use cases that we see include online use cases like being able to feel texture for a product purchase, like Amazon kind of thing. And then immersive media experiences. Perhaps some of you had a chance to try a D-Box theater experience where the chair itself is on a motion platform and incorporates some kind of vibration feedback into the experience. So these are all in the general domain of haptic use cases from a media perspective. Probably the most well-known haptic use case, at least in the immersive domain, would be the Sony PlayStation 5 controller. And this just came out in December and really has some really nice haptic qualities associated with it. It has two different types of haptics in it. There's actually a force feedback. So there's a resistive trigger on this device, which you can't really see here, but it's on the side. And then there's a high definition vibration voice coil. There's actually two, one on each side, that provide kind of an audio-like fidelity for vibration experiences. And so if you haven't tried this, I definitely recommend it. Certainly in the domain of immersive media experiences, it's pretty well known that adding tactile feedback of some kind increases the sense of presence and the sense of involvement. And those are sort of two different things. I just cited one example paper here. There's literally dozens of these things that we can look at that show the relationship between a control scenario that's visual and auditory only, that same scenario with the addition of passive haptics, which would just be a non-actuated haptic prop, and then the addition of other types of haptics here, which could be dynamically controlled. And so, you can go check that out if you like. So when we started thinking about, is this domain ready for standardization, or what's the perspective we should think about? Certainly at Immersion and at InterDigital and
Apple and so on, we've, all the working group members, we look at a whole bunch of different possible use cases or configurations, I should say, of endpoint devices where there's haptic opportunities or there's likely to be haptic feedback mechanisms available. So a common one that we see is a mobile phone, which is shown here, and or possibly including headphones. And those headphones can also have a haptic dimension associated with them in terms of a vibration channel. We also see similar configuration now, but maybe with a gaming chair. So someone, playing a PlayStation game controller, a gaming chair. Now you have, 1, 2, 3, 4, 5, 6 different channels of possible haptic output or endpoints. You could also have a similar thing, but a desktop configuration now with a keyboard and mouse. And so now you have these different haptic endpoints here. Also, they could be vibration, they could be force feedback. There's various ways that those could be configured. And then in a fully immersive environment, you might have a vest, you might have haptics on your head-mounted display, you might have haptics in your shoes. And so as a content creator, this is kind of a disaster from trying to figure out how to generate content that can be rendered appropriately across all those different configurations. And this is really sort of at the core of what we're trying to get at with our MPEG track in ISO, sort of with our haptics track in MPEG. To give you a little bit more character or feel for what this looks like from a media coding perspective, there's 4 or 5 different distinct haptic modalities that sort of matter or that are going to be relevant in the next 5-10 years. The first and most common one for sure is vibration, and I think everyone is familiar with this. This is your mobile phone actuator that vibrates, but also the dual shock or dual sense voice coil style vibration, which is vibration effect in time. From a media perspective, you can think about these as being similar to kind of wave files, like just PCM coded time series, or perhaps more appropriately, something more like MIDI. Because the thing which is notable about haptic signals is that they have typically low duty cycle. So you don't normally play them continuously. And so encoding them as something that's more parameterized often makes more sense than just coding a time series. Compare that or contrast that to those gloves I showed you earlier, which actually have a spatial array of pneumatic actuators in each fingertip. So each fingertip has an array of these kind of pneumatic cells that raise and lower programmatically. That looks a lot more like a depth image that's rendered on each fingertip. So from a media perspective, you'd be thinking about how do I create a depth image for each finger? So I would have 10 channels of depth images, for example. Another device, I don't see a lot of this in immersive media, but it's certainly not impossible that you could use it, is like a friction display. So this display here, actually, when you move your finger on the surface of it, the friction can be modulated up or down. And so the way that you code that is typically as a 2D grayscale image where the bit value encodes the amount of friction you want the user to experience at any point on the 2D array. And then finally, the sort of 3D devices like the Geomagic Touch, this is a haptic robotic armature that you hold onto here, or the triggers on the PS5 DualSense. Those require something which is a little bit more model-based. And so think about, like, for example, geometry with mechanical properties. So I might have like a surface, and that surface might have a stiffness associated with it or a mass or something like that. And then I use a model-based rendering function inside the device to actually create the experience. So what that tells us, at least, given that we're at the requirements phase, is that there's a couple of unique challenges that are somewhat unique to haptic media. The first one is that there's no single device that can generate the entire range of perceivable tactile sensations. What this really means is that, think back a minute ago, all those different devices, they have different media encoding possibilities. They have different sensory channels into the user's brain. There's actually 4 different types of mechanoreceptors that the human body contains, and they all have different sensitivities, different perceptual thresholds, different frequency ranges, et cetera. And there's no device that exists today that can render all of those things on any location on the user's body. The second one is the variability of tactile sensitivity is orders of magnitude over the surface of the body. So your fingertips are vastly more sensitive to tactile stimulation of a certain type than your back. or then the top of your foot, or then the side of your ear. And so this variability actually changes the type of actuators or the type of rendering, mechanical rendering configurations you want to utilize. And it also changes the way you would probably want to code for those locations. And then in addition to that, if that wasn't enough, in addition to that, you have these effects which are called priming and masking, which is that the perceptual sensitivity of a specific location depends on what happened before. And so you can actually change the sensitivity by playing certain types of effects, 500 milliseconds ago, that will change the sensitivity of the user to subsequent effects. The other thing is the representation of the physical body inside the immersive media domain. So normally what I see is a head that can be oriented, for example, for 360 video or for, and 6-off media. We need to add meaningful pieces of the user's body, like their hands and their arms, and then have the right amount, the right kind of mapping into the immersive space so that you can do collision detection and identify where the effects need to go. Oh, sorry. And then once you have some notion of where the effects are to be driven, you have to actually map those onto individual physical devices. And as I showed earlier, there's a bunch of different kinds of devices, and they're all from different manufacturers. They have different interfaces. And this causes a lot of complication for middleware platform level APIs. And then some types of feedback require closed loop control, which means there's a sensor driving a model that then generates feedback, and it has to run with very low jitter, like 1 millisecond plus or minus 1% kind of thing. And some of them, like time dependent stuff, vibration and so on, is a lot looser in terms of its timing requirements. And then in addition, there's a strong influence between other modalities and haptic perception. People are not used to having pure haptic experiences in general. And so the brain is naturally pre-attenuated to, or sort of pre-attuned to integrate these different modalities. And there's different ways that you can actually utilize that to gainfully influence perception, but also perhaps to do some kind of interesting compression. And then finally, I think this is the topic Ahmed was going to talk about, is interactivity. This is probably the most important consideration, at least for our future work in haptics, because haptics is fundamentally an interactive experience in the sense that you have to go and interact with some virtual media in order to have a touch experience. And so how we decide to standardize an architecture and architect the interactivity portion of our immersive media standards is going to be incredibly critical for haptics. And these two things should result in an open, clear communication between our different groups. Finally, we're currently starting to look forward to phase 2. This is a very simple architecture diagram that we put together, essentially identifying haptics as being something that could go into the presentation layer. I'm not going to dwell on this. It's still extremely early in the process. But I will point out that in the working group or in the ad hoc group, we've decomposed the haptic standard into a phase 1 activity, which is actually at the end of testing right now. We expect to report out test results from 4 proponents in a couple of weeks in an October meeting, and that's focused mainly on time-dependent haptic experiences. And then phase 2 activity, which we're sort of just starting on now, which is really more related to interactive and immersive experiences, where there's some relationship between user body pose and the haptic feedback that they get. And that's something that, as I said, we're just kicking off, and we look forward to any and all inputs related to that. And with that, I will wrap it up, hopefully on time.
Absolutely perfect. Thank you so much, Chris. I am sure there will be a couple of questions. Still, I would like to get the 3 MPEG talks done, and then we go into a bit of a discussion. So Chris, stay tuned, and I'm checking with Skylar, if Skylar would be available.
Yeah, I am available right now. And,
hey, Skylar, our MPEG audio convener, W26 convener. So Skylar's going to talk about audio, which we had a bit of discussion in the first presentation yesterday, but I think there is more detail here. The audio.
Okay, so you see the screen, everything's good?
Yes, perfect.
Okay, so thank you. I am convener WG6 MPEG Audio Coding, and I'm also with Audio Research Labs. And so let me go through. First, just to get everybody on the same page, what is audio for immersive experiences? So we have 6 degrees of freedom, XYZ, yaw, pitch, roll, and we imagine this is through physical body movement. So not so much like a gaming chair, but we're going to move through a virtual world, or certainly through an augmented reality experience. And we want to have this experience, okay, be virtual reality, augmented reality, which would typically mean in the VR case, we wear a head-mounted display and headphones. And so we have to have this audio technology position virtual sources in a VR or AR world. And to render those sources with localization, possibly occlusion, reverberation, directivity, and diffraction. So those are the primary mandates or technologies we have to realize. Localization, we have our head, sounds come from over here. We have a head-mounted transfer, a head-related transfer function, and it has cues of relative to the 2 ears, time arrival differences, level differences, and coherence, which is primarily due to differences in reverberation. So that's one key and pretty straightforward technology. Sources have directivity, so there's some directivity map shown here. Just to say I'm talking to you, my voice is louder in the front of my head, softer if you're behind me. Pretty simple, but very important. There must also be ambience and reverberation. So ambience might just be the sounds around, the crickets and the outside, for example, but almost all spaces impose some level of reverberation. So we need to simulate this. And we have a model for virtual reality, and we'll touch on that really as the main part of my presentation. But really interesting in terms of collaboration is in augmented reality, we have to estimate a room's model for reverberation. And how would that happen? Maybe through AI and a visual examination of the scene. We have that as out of scope, but this is a very interesting domain for collaboration. We also need to simulate occlusion and diffraction. That's kind of like going around the corner from a sound object. So the technology in MPEG-I audio is first audio compression, but we're going to use the recent standard MPEG-H 3D audio, so we have no new audio compression technology. What is new is we add MPEG-I metadata to some bit stream that carries both the new metadata and already standardized compression engine. And then we add in the decoder, after we get the audio back from the MPEG 3D audio decoding, the audio rendering technology of localization, directivity, and we could use parametric models for reverberation and other effects, or we could possibly use ray tracing. So what I really want to talk about is what in the current point in our standardization, an encoder input format. This is the format for all information needed by the MPEG-I call for proposals. And that's really, think of it as the proponent has an encoder for all this audio technology. It says for a scene, there are audio signals and what they are, metadata for signals, position, orientation, directivity of an object that's emitting sound. But now, interesting, the room information. The walls have acoustic properties, transmission, reflectivity, and animation, which could be moving objects that have all the properties here in audio signals. And this is a hierarchical scene description, like a scene graph. So this is basically our proto-audio scene graph, and it's expressed in XML. So let's see what that looks like. Here's an example of an audio object in this encoder input format. It's a trumpet. And here you see the XML expression, but essentially it's saying a trumpet has a position in space. It has an orientation at that position. It has a directivity function, and it has a gain. And further, it's a continuous signal. And we'll see that there may be interactions which are not continuous signals. And this would be a streaming sound from, let's say, some server to the client decoder. We also have the room acoustic model. So it defines a room. It has a geometric model of, let's say, triangle meshes. Triangle faces have acoustic attribute label, let's say upholstery, and then this upholstery has frequency-dependent properties, reflectivity, absorption. And this is the XML expression, and it can get quite detailed. But this is important because, again, this is the virtual reality world, and this defines your world in an acoustic sense. We can also do scene updates. So imagine there's a car and we have three sources, engine, two tires that we can see. And the point is these should be atomic. The car moves as one unit. And we want to support the fact that there's some updates in our scene. And so that's part of our scene graph also. And in addition, there is updates due to interaction. So in this virtual reality world, the user can open a door, the handle might have a sound, the door opening might have a sound. These are labeled as an event and they trigger a cached sound to be played out. And so that's also expressed as an option in the EIF, such that if you take your wand and touch the handle, things will happen. So we're now on the verge of evaluating technology. That will happen in January. I'll show you a timeline in a moment or two. It has, let's just take the example of the immersive virtual reality world. It requires audio and visual presentations because we want it to be really immersive for the subject. So correctly perceiving the virtual audio world without any visual cues is very difficult. So we will evaluate audio technology using a full real-time audio-visual 6 degrees of freedom presentation. And the motion will be with full body motion. So the user moves the body rather than just a joystick or anything like that. You walk around in a space. The head-mounted display is driven by Unity for the visual presentation. The headphones are driven by Max, MSP for the audio presentation. And the proponent technology runs as a real-time Max plugin. And it might look something like this. So we see this virtual world in our head-mounted display. We have a bus that is a sound emitter. We can have people that are speaking. Over here is a little guy that's playing the bongos. And so that's another sound source. And there may be reflections off these city walls. And so and it's static, but now you could explore that scene. That's an example of the kind of virtual environment that we're actually using in our call for proposals. And speaking of that call, I want to wrap up with the timeline for standardization. So we have the call out in April. We will evaluate in the January meeting next year. And from then we will pick technology, do some core experiments. We'll have a verification test. And then in about 2 years, we'll be done. And we hope that this is for the rendering technology. We hope that as a companion to this is something about the audio scene graph, and that's still a little bit up in the air, and we'd be happy to work with, obviously, the systems group to bring that to a standard, to issue that as a standard. Okay, that's what I wanted to talk about, and thank you so much.
Yes, Kyla, thank you so much. So I think that is helpful as well. So I would hand over to Imet, who is ready now, and then we come back to discussions on audio haptics and MPEG phase 2. If you would stop sharing, Scala, I think then.
Okay. I'm out now. Thank you.
Thank you. But stay tuned, Scala. Thank you.
Yep.
Thank you. Let's see if it works out this time. Yeah. Okay. Hopefully you can see my screen and I can switch between slides.
Oh, good.
Which is good. Yeah, so I see we are running a bit behind schedule, so I'll be really quick. So I said, the features we left for phase 2, which are actually quite important features based on the use cases we have, are interactivity, and we heard from Chris and Skylar on like these different features, like for instance, triggering some audio or haptic feedback when a user collides with an object or stuff like that. So being able to signal like characteristics of the different objects in the scene in order for like the renderer to be able to build like a collision or maybe feed it through like a physics engine and build like a collision model so the user can interact properly with the scene. For instance, user should never be allowed to walk through walls, or when the user bumps into a chair, maybe the chair doesn't move at all, is static, or maybe the chair gets displaced. There is some feedback, for instance, maybe that can be triggered to inform the user that, okay, he or she bumped into an object. So binding in and describing like this type of feedback is all like part of this interactive experience that we want to offer or enable in a scene description. So that's one way. The other way is basically to control how the camera moves along the scene. So the user, or maybe by author's intention, should not be allowed to move 100% freely around in the scene, which is what we have currently. But the author might want to limit the position and directions of the viewer, where the viewer can be located or can be looking at. So that's something that we can achieve also through controlling the camera by defining like paths. We are still discussing how to define these volumes for the paths, so the places where the user, the viewer can be located. So all of this is ongoing in phase 2. We have some basic agreement that we want to support these two types of interactivity. So that's documented in technologies under consideration. So ultimately, the amendment to the spec will have some solutions for these two approaches. The next and big topic we want to support there is integration with XR. Of course, we value the work that Khronos has done on OpenXR. It's really very good foundational work that would democratize access to the XR technology, and we want to leverage that. So we want to be able to anchor like a 3D scene that is described through in glTF into like the user's real environment. So by selecting or helping the user or the application to select a reference XR space, and then placing like the scene like with the correct scale, with the correct orientation, and positioning in, on that or with reference to that XR space. So that XR space could be like the viewer's XR space. So one of the reference XR spaces that are defined. So for VR, it would be just the viewer's XR space. It could be like for AR, it could be like stage or something like that. But we want also to enable like applications to define their XR spaces. So that's a feature offered by OpenXR. So we want to assist or convey like sufficient information in the scene description so that the app can select and create its application-specific XR space and anchor the scene to that space. So these are things we're investigating at this point of time. Again, this is still work in progress. Something we started looking at, and of course, interaction with the OpenXR experts and the glTF experts. Of course, the 3D formats experts would be very appreciated and could have like also like a shaping impact. So since we are really still at the very start of this phase 2, like other things we will integrate in phase 2, and I talked about the architecture, like the 2 interfaces that were still missing and left for phase 2 are the local interface and the interactivity interface. So for the local interface, we should be able to bind like local input, for instance, from cameras, microphones, help with maybe applications that want to do like scene understanding. For instance, you want to identify a certain object in the scene and build an XR space around that and anchor your scene based on that. So having that these camera feeds made available and maybe sent even to the network for processing and scene understanding or split rendering, things like that is an important feature. So we want to be able to send streams, metadata streams, but also media data streams. Like metadata could be pose information, for instance, for to support like split rendering and stuff like that. Of course, haptics and like 6DoF audio or MPEG immersive audio are on the roadmap. So support for more advanced audio, like what Skylar talked about. I think we will work with the audio group to integrate that. And then whenever it's ready, in probably phase 2, maybe that can extend beyond. So depending on how fast the 2 projects will run. But haptics, definitely, I think that's a key component of interactivity. So that will be integrated in phase 2. Yeah, I think that's pretty much all what we have, or at least what we know so far. We want to have in phase 2. Of course, this is still less mature since it's in the early phases. And we, as I said earlier, we appreciate any input from Khronos on these topics. Yeah, thank you. I think I'll stop here and we can take questions.
Yes, Imad, thank you so much. Despite a bit short of time, let's dedicate up to 5 minutes again for the discussion on what's happening in MPEG on haptics, audio, as well as the phase 2. I believe that's worth it. And then we just take this away at the end. So let me see, are there any questions or comments on the presentations from Skylar, Chris, and or Imad? Please raise hand. So maybe a bit for Khronos people, I would like to, what I think is a continuous questions we had is other senses than visual, right? So audio and haptics, to what extent is Khronos looking into this for integration into the environment? Is there anything that you, Neil, or anyone else can say anything about?
I think the main API where the Khronos activities are converging on that is OpenXR, which is the next session. So I suggest perhaps it would be actually interesting to go through Brent's OpenXR update, and then we can look back on the MPEG side and the OpenXR side. That might be a good way to structure this.
Yeah, that makes sense. I have a question from Max.
Hey, sorry, I can't share camera right now. I just came from a run. I also have a question for Skylar. If there's already a tightening on the proposal, is this mainly object-based, channel-based? Is there any kind of preferences already towards the immersive audio encoding that you are looking forward to evaluate?
So primarily, objects are point sources, or maybe sources with some extent. So mostly everything is a mono channel, but it's really at a position, and we'll call it a object. We have, in addition, higher order ambisonics for ambiance.
Thank you. That makes sense.
Thomas, if I could, I would just comment that relative to OpenXR, there is some early discussions on haptics in the OpenXR platform group, but it's at very early stages. And so I think we're looking forward to finding the right connection between the MPEG work, particularly the phase 2 work, and the structures that may need to exist on the platform side in OpenXR.
Okay, good. Any more questions or comments on what was presented? I always need to search for my participants list if I missed anyone. It doesn't seem so, but I think we have a natural transition to the OpenXR presentation. We have another Brent from Intel, OpenXR chair. So I think that's a good idea. Maybe we can then come back again, how OpenXR fits into these discussions we had now. So Brent, please go ahead. Thank you.
Okay, thanks, Thomas. So my name's Brent Insko. I'm lead XR architect at Intel, and I'm the OpenXR working group chair at Khronos. So today I'll spend a few minutes talking about OpenXR, what it is, and some of the latest developments we have going on there. So I'll talk about what it is, why was it needed, what's been going on, and where are we going next with OpenXR. So OpenXR is a royalty-free open standard that provides high-performance access to augmented reality and virtual reality platforms and devices. And so what does that mean? So OpenXR handles the communication to and from an application and an XR platform. And so an XR platform such as the Valve Index, the Oculus Quest, or Microsoft HoloLens 2 provides the application information such as the head and hand position, information about the controllers and the input states, such as what buttons have been pressed and released, and also display configuration and form factor, such as whether there's a single display or multiple displays. The application provides the XR platform, an image or images to display, provides the audio information, and also provides any haptic responses, such as vibrational responses to the controllers. So why was OpenXR needed? So consider the variety of XR platforms that are available. They range in display capabilities, tracking capabilities, environmental input capabilities, as well as controller styles and input mechanisms. So before OpenXR, with so many platforms, they were all driven by proprietary software interfaces. It increased development time and the cost for application developers trying to reach a broad XR audience. Separate code paths had to be developed for each of the platforms, and then you had to validate, make sure all of those worked on all the different platforms. And this fragmentation really increased the cost and developers' time, and would prevent them and developers from working on other titles and other platforms. So with OpenXR, applications can now program to a single common high-performance API which support all the major VR platforms and many of the AR platforms out there that are available today. So OpenXR contains everything an application needs to drive an XR devices in the system, including the device discovery, event processing, sensor tracking, and pose calculations on the input side, and frame display timing and composition, plus haptic controls on the output side. You know, OpenXR is used alongside a rendering API, such as the Khronos's Vulkan API, to generate imagery. OpenXR can be used with any 3D API, but a new generation API such as Vulkan, which we've talked about here in some part, is particularly well suited to create applications with high rendering performance and the low latency that are vital for compelling XR experiences. OpenXR is an extremely flexible API. It supports both AR and VR devices. It supports both devices tethered to a PC and all-in-one standalone devices. And it also supports devices running on different OSs, such as Android and Windows. This is a high-level overview of a possible OpenXR application. It's just to give an example of what the flow of a program and the steps involved. We don't have time to get into the details today, but you can go to our landing page, openxr.org, and our GitHub repositories and find out more information about the details of OpenXR and more sample code. OpenXR continues to accelerate its growth. We began development of OpenXR in early 2017. 2 years later, we released the 1.0 specification after developer and community feedback from a provisional release. And then last year, we released the Conformance Suite and launched the Adopters program. Since then, we've seen more and more XR platforms adopt OpenXR, and most recently, we're seeing applications take advantage of the cross-platform support of OpenXR. So let's talk about some of the latest developments with OpenXR. So as the title of the section implies, OpenXR can now be found on an HMD near you. In fact, all of the major XR platforms currently have conformant implementations of OpenXR. They include the Microsoft HoloLens 2 AR device and their Windows mixed reality headsets, Oculus's all-in-one Quest and Quest 2 headsets and their PC-based Rift S headset, and the HTC Vive Cosmos headset. We've also had more recently had adoption across even more platforms, including Valve support on Steam VR, which would, of course, bring along support to a wide variety and a number of different VR platforms. Vario supports it across all of their headsets, and we now have an open source runtime provided by Collabora's Monado runtime. We also have support across the two major game engines, Epic's Unreal and Unity. Beyond just supporting OpenXR, all the major platforms have publicly announced that future developments on their platforms will take place on OpenXR rather than their proprietary API. So really, as application developers look to see where and how they're going to develop their applications, OpenXR is really the future for all of the future, is really the future on all the major VR platforms. So now let's look at some of the applications that are beginning to use OpenXR. So Minecraft will use OpenXR to provide VR support across OpenXR devices. Microsoft has also launched VR support in their flight simulator application. Blender, the open source 3D rendering engine, has incorporated OpenXR for use in their VR scene inspection. OpenXR is also used across all the Chromium-based browsers for supporting WebXR, the browser-based XR API. So both Microsoft Edge and Google Chrome support WebXR using OpenXR. And this is just an example of Blender and the ability to use VR to do scene inspection as you're developing scenes using the Blender application. We also have, excuse me, we also have a major franchise game that just launched within the last few weeks that uses OpenXR for cross-platform support. Zombieland VR, based on the movie, is a game built using the Unity game engine with OpenXR support in a single executable that can run across all the major PC-based VR platforms. So what's next for OpenXR? So while we had a stable core OpenXR API, which we released in 2019, we continue to add and support and explore new AR and VR features through extending the core API. OpenXR follows the same extension process as other Khronos standards. So you have kind of a core standard, and then you have a variety of different ways that you can extend the API based on the coverage and the number of platforms that are going to support the extensions. So when we launched in 2019, there were 16 extensions that were released in conjunction with that 1.0 release of the specification. And today we have 72 current extensions. These extensions show that the companies involved in OpenXR are using the core API as a base to extend and expose new capabilities that are part of their platforms. There are also extensions exploring where OpenXR may go next, such as scene understanding and spatial anchor extensions. So while the core XR API 1.0 API may be not changing very rapidly, there's a lot of work being done on top of that solid foundation to explore and get experience with what the shape of the APIs of the next set of features coming to OpenXR should look like. So let's take a look at a few of these extensions that we've been developing. So one of them is overlay support. So overlays allow multiple in-world applications within OpenXR. This allows one app's 2D content to be layered on top of an existing application's content. This enables rich content into other XR applications. Use cases include, displaying the desktop OS window in your XR world. It also enables, video chat while traveling between planets, as shown on the right. We're also expanding user interaction capabilities. One of these is real hand tracking. The hand tracking extension standardizes the joint positions and orientations. And it may not seem like much, but it represents a number of months of work among a number of companies who already had hand tracking capabilities to kind of unify and figure out what should the standard look like so that applications could take advantage of hand tracking capabilities across all of their platforms. And just a really quick video demo of, let me click here, of showing an application using the OpenXR API along with Ultraleap. They developed an API layer to do hand tracking running on Windows Mixed Reality. Along with hand tracking, we're also pushing other advanced UI capabilities such as eye tracking. We have eye gaze interaction to build more intuitive interfaces and allow for natural aiming within applications. OpenXR is also looking to the future of the location of computing and providing portability as AR is deployed on new platform architectures, such as edge servers. So one architecture being developed is uses 5G to connect a lightweight AR device to send its real-time sensor data back to an edge server that processes the sensor data and generates graphical augmentations. And this would allow much more sophisticated augmentations that would be allowed on such a lightweight device. The OpenXR API can basically make it look like a native application. So you can develop your application and hide basically the platform implementation underneath. So the application could run natively. The same application could run natively that could run on this AR device, a lightweight AR device talking to an edge server somewhere else. So what's the future of OpenXR? So we're working on fixing some things from our 1.0 release. We're also expanding support for AR and MR. So we're looking and have been spending a lot of time looking at scene understanding and what makes sense to expose to applications. And as was mentioned earlier here, haptic support is one of the things we were in early stages discussions about. We're also looking to expand body tracking support and additional controllers and device support. So as I said before, OpenXR is on an HMD near you. It's on all the platforms. Now's the time to get involved. We have officially conformant runtimes from all the major platforms, and it's being used by real software, real applications today, from Unreal and Unity game engines to Blender to Chrome and Edge, Flight Simulator, Minecraft, and we're seeing more and more games use it as well. We have widespread industry support. The number of companies that support OpenXR continues to grow as they see the benefits of developing AR and VR applications and in a cross-platform manner. One of the reasons that OpenXR is gaining such wide industry adoption is that it's a win-win for all involved. The software developers win because they can write an application once and ship it on multiple hardware platforms without reporting their code, saving time and money. The XR hardware vendors win because if they expose the OpenXR APIs on their platform, they will have access to more and more OpenXR applications as they get developed. And most importantly, the end users win, as they know the XR applications that they want to run will run on the and will be compatible with the OpenXR devices that they have purchased. So with that, I think I will conclude, and thanks everyone for listening. And I don't know, maybe we have some time for questions. Thanks.
Brent, thank you. Thank you. I believe let's throw in 1-2 questions here, but you had a great great transition to the 5G discussion as well with one of your slides. But let's check. Let me see. I don't see anything being raised. Could you go to, I think it was page 32, where you did this networked OpenXR?
Sure.
Maybe, or maybe, yeah, here we go. Here we go. Mm-hmm. So what you basically have, you're networking the APIs. That's what I understand, more or less, right? So how much is this just a conceptual vision, and how much of this is available in OpenXR, for example, understanding the formats, the protocols, the data rates, the frequency, the KPIs? That's what I get questions on. What is low latency here? How much data rate is it, like gigabits? Are we talking, and so on? What is the compressors we need, and so on? So all these questions. How much is this concept here a vision? How much is there implemented? How much is Khronos doing themselves? How much do we have to collaborate here? I think that's a question I would have now, but maybe we can also have it as a discussion later, just as a starting point.
Sure, and I would say it is becoming real. There are real companies backing this and trying to figure out, what makes sense. As you were saying, what are the details? How much latency is tolerable? You would have more than likely a split of the rendering, right? You'll probably have some amount of rendering, lightweight rendering on the headset, and while there's potentially, the heavier weight done at the edge server. And I have gotten this question at other conferences too, talking about OpenXR with 5G. And really, OpenXR is about building the application in a portable manner and hiding the underlying platform. So OpenXR isn't building or determining, what are the right rates or what are the compressors. It's really about building the applications portably, and then that allows the platforms that are being developed to utilize OpenXR applications that already exist, plus the ones that are going to come. But I do know a lot of the member companies of Khronos that are participating in OpenXR. They're very interested, and there is active development in this area to varying degrees of completeness and moving out of the lab.
Thank you, Brent. Any other questions for Brent now? No, so I would like to take that slide as a transition to Frederick and Gilles for the for the presentation what 3GPP does in this area. And so I hand to Frederick and Gilles. I don't know who's going to give the presentation, but I leave it up to you, and I think both speak at the same time or leave slide by slide. I'm sure you can
We'll
manage
try
that
to speak at the same time.
Go ahead, and I
Thanks,
think we're good in
Thomas.
time, so we will just have a wrap up at the end. So please take your time. What needs to be said should be said. Thank you.
Okay, thank you very much, Thomas. So I will share the presentation. I'll share the first few parts, and then probably the conclusion, and the bulk of it will be given by Gilles. So I'm Frédéric Gabin. I'm at Dolby Labs, but presenting here today as chair of the 3GPP SA4 working group. So we'll be presenting an overview of 3GPP activities related to extended reality together with Gilles Tenu from Tencent, who's the vice chair of SA4 and the chair of the SA4 video subworking group as part of SA4. And the video subworking group deals with these matters of XR. Next slide, please, Gilles. So this is probably just the content, and we don't need to spend time on this. But the next one, I guess, if you go to the pyramid, I guess you've heard about 5G, and if you haven't, please let me know on chat. We like to present 5G as a platform that enables current and future applications and services, whatever they are. There are two key building blocks in 5G. One is the 5G new radio that's capable of up to very high bit rates in both downlink and uplink, together with low latencies in a flexible manner that matches the quality of service requirements of the applications. Another key building block is the core network architecture that is so-called service-based, so natively ready for network function virtualization, slicing, which means virtual networks for particular applications, cloud and edge computing applications, including private 5G networking. So this classic triangle that you've probably seen many times, the view aims to visualize the three main directions of expansion of cellular standards from 2G to 5G, or from 4G, which was mostly voice and mobile broadband at the top, so high bit rates, to further directions, ultra reliable and low latency communication, so and massive machine type communications. The XR application, they lie between mobile broadband at the top and the ultra reliable low latency communication at the bottom right of the triangle, which require high bit rates in both uplink and downlink, as well as low latencies. And of course, that depends on the particular application we're talking about. Next slide. So this is a bit about 3GPP process. 3GPP works in releases where specification set are complete within a release, and they're constantly evolved with the next release in a backwards compatible manner with new functionalities depending on business needs and the features that are required by the industry. So the 5G was first delivered as part of release 15. Obviously, the previous releases were 4G and 3G. It was delivered in mid-2018, and release 16 has been completed last year and has all the fulfills all the 5G requirements that were set by ITU. And we're now under release 17 that's running until March next year. So we'll be completed in March next year. And release 18 has been started. It's so-called 5G advanced. So we're not there yet on 6G, but we're reaching 5G advanced. So the service requirement phase is going to complete in December, and then the specification work will last until the end of 2023. Next slide. So 3GPP has a three-stage approach where, and that's I want to picture this such that you you know where SA4, the Multimedia Codecs Systems and Service Group, is within the 3GPP process. So first, there are stage 1, which are service requirements that are defined by a dedicated group, which are input to architecture work that mostly happen in the SA2 in the architecture group, but also in the mission critical application group in SA6 and part of multimedia architecture parts in SA4. We have RAN, Radio Access Network Working Group, that interact with SA4 when it comes to quality of service, cross-layer optimization, advanced media type support. And finally, the core network and terminal protocols and coding groups, which are focused on stage 3 interface definition at the implementation level. Next slide. So lots of words to describe the activities that are related to XR. In 2018, in SA4, there was a part of release 15, a first study focused on virtual reality. We had a number of workshops, and a TR was produced, 26918. And by the way, all these documents are public and available on the 3GPP website. And a technical specification on virtual reality media profiles for omnidirectional 3DOF media was also approved. In 2019, that's release 17, the stage 1 service requirements were issued, the TR in 22842 for network control interactive services, including cloud gaming and VR applications. So these service requirements are in force in release 17 for 5G. So 5G should support these applications and the connectivity for these applications. In release 16, we had a further study documented in TR 26928 in SA4, but this one on extended reality, so beyond VR. In 2020, release 17, we have stage 2. So that's the next step after service requirement is to define architecture and protocol aspects, where stage 2 decided to specify new standardized 5QI values. We have a slide on this to support these advanced interactive services. So that's the first step to support those specific quality of service. And then in 2021, there are activities in SA4, the ongoing study on typical traffic characteristics for XR that comes into support of the radio access network group study on XR. So there are dedicated study work happening in the radio group as well to support XR and consider device power consumption, capacity coverage, and mobility in the type of scenarios that Brent actually described in his slide. For split rendering, for example. And then there's the ongoing study on 5 class type augmented reality, mixed reality devices, and Gilles will give more details about this one. Next slide. So these are the 5 QIs. They're QS index, and these are the new ones that were defined for XR, where you can see a priority level, a packet delay budget, which accounts for the delay between the device and the gateway to the data network. So that's mostly radio, and some of it is packet core. Some bursts, some averaging window, and the example services, in that case, the motion tracking data and visual content for cloud, edge, or split rendering. Next slide. We've, of course, in the course of our standardization work, tried to be accurate in the definitions. So I won't read those. You probably know them already, but it's good to be clear what these terms are. And then I'll go to the 5G media streaming part, which is really something that was an architecture that was defined in release 16, where we have a specification 26501. It's been it supports services for the mobile network operators, as well as third-party services for downlink and uplink media streaming. So that was the focus at the time. And this architecture, so the media architecture are the yellow parts, the gray parts are the core 5G system architecture, and the blue parts are outside the scope of the specifications. It's divided into independent components, enabling different deployments with various degrees of integration between the 5G mobile network operators and the content providers. So these are extensions to the 5G system, enabling several collaboration scenarios that we actually describe as guidelines in the specification. The application function and the application server functions, they're data network functions that communicate with the so-called user equipment, that's the device. And the application function can leverage 5G system functions to enable particular policies, for example, associated with the content or service in coordination with the policy and charging function. It also enables QE, metrics reporting, consumption reporting, network assistance. That's also supported for these types of services. The user plane, the data, the dash, streaming happens between the application server and media stream handler, and the media session handler is the device part that communicates with the application function to enable all these 5G functions. Let's move on to the next slide, where there's ongoing work for the edge computing extension. So a study work has been done, and the normative work is ongoing as we speak, where the objective is to map the 3GPP generic edge computing architecture onto the 5G media streaming architecture. And the edge computing enables application storage, computing execution as close to the user's device as possible. So we can enable lowest latencies, possibly keeping data secure within premises, reducing the backcoding capacity requirements, improving reliability. And it also opens up for split rendering applications as well. So here, the orangey part are the ones, the orangey parts are the ones that are the core edge architecture mapping to the 5G MS architecture. And finally, before I hand over to Gilles, in the next slide, you will see the ongoing study work on XR, a simple mapping, and that's again part of the study phase, so nothing normative yet there, where XR functions are mapped to the application function and the application servers in this 5G media streaming architecture that is meant to be scalable and extensible. And now I should give the floor to you, Gilles, I guess.
Okay. Thank you, Frederic. Hello, everyone. Well, let's see now how 3GPP initially addressed extended reality with the study called FS5GXR. And this study was triggered to primarily put a definition behind extended reality and identify what it means in terms of quality of experience. So we collected a large number of use cases addressing different types of consumption, streaming, conversational, interactive, as well as representation formats and candidate technologies. And all the findings, as mentioned by Frederic, are documented in a comprehensive technical report, the TR 26.928. So I invite you to have a look at it if you're not familiar with it. As said, we provided a list of definitions in terms of degree of liberty, reference coordinate systems, definitions of concept of presence, formats also such as meshes and point clouds, pre-rendering techniques like asynchronous time warping that are implemented in ultra-low latency environments. And here is a list of use cases identified with their associated type of reality, AR, MR, DR, the degrees of freedom, the type of delivery, and also the target device. And the technical report contains for each use case an analysis of the feasibility, some example of existing services, if any, and as well as potential standardization needs. And as part of the study, it was also important to categorize devices depending on their functionalities. And some devices rely on external entities for some processing. Others are fully standalone in terms of media processing, but also in terms of connectivity. Some aspects addressed were latencies and delay, with some requirements identified depending on the scenario. On the latency, for instance, although we identified that less than 20 milliseconds motion to photon latency was required from the time you move your head to when you see the display change. We have listed requirements for ultra low, low, moderate, and non-critical latencies. We have also identified technical requirements for visual presence. For example, for spatial resolution, 2K by 2K per eye was required in order to provide acceptable quality. 4K was considered as next step, and 8K as the ultimate goal. And for temporal resolution, a sustained frame rate of 90 Hz and beyond is needed despite the usage of asynchronous time wrapping process, for instance. So here is an example of a split rendering architecture in which the pose of the user is sent to a server that may be located at the so-called edge or a cloud entity, and computes the scene to be rendered and send it back to the user equipment for rendering in a timely manner. And finally, we decided to consequently launch more activities such as the development of a framework for split renderings, the extension of multimedia telephony for enabling services, and also the documentation of XR traffic characteristics and the focus on class-based AR MR services that I will explain in the rest of the presentation. So a few words on the traffic characteristics for XR media over 5G. The study was launched more than a year ago with the objective to collect traffic characteristics for immersive media services, including downlink and uplink data rates, taking into account delays and packet error rates, and deduce the impact of quality of experience when such media cross the 5G network, which is kind of a challenge due to the complexity of simulations and the many parameters to be incorporated. And some options were to rely on realistic system setup with measurements, or to measure existing services, or even to break down the system into smaller pieces. But some approaches are impracticable due to obvious complexity aspects. So the basic challenges here are really to evaluate the basic system design options and their performance, to generate traffic models for the evaluation of the radio access network options, and to provide guidelines for good parameter settings and on encodings, content delivery, but also on the network operating configurations. So we finally decided to define traffic models using source contents that are converted into video traces. So these are the V traces in gray in the figure. The encoding configurations associated to different scenarios allow for the generation of simulated traces, the S traces in blue, that are converted into P traces in orange. And those P traces incorporate content delivery models. Those traces are then shared with 3GPP radio access network experts who will apply different network QoS parameters indicated by Frederick earlier, such as latencies and packet error rates. And 3GPP SA4 will then run the inverse process, and we'll have to define a model for evaluating the impacts on the perceived quality. For instance, if we realize that a packet associated to an intra-frame has been lost or has arrived too late, the consequences on the perceived quality won't be the same as for a non-reference picture. On 5G Star, 5G Star is the ongoing study on glass-based AR and MR services over 5G. This recent study has the objectives to address the following points: to identify the functional features of AR glasses, to focus on a limited set of use cases from the initial study on XR over 5G, define the architecture and media flows, identify also the representation and distribution media formats that are exchanged between different equipment, and also to identify the content delivery protocols and the capability exposure. And during our study, we identified the need for differentiating device types depending on their functionalities and connectivity. And the two main types are STAR, standing for standalone AR, and EDGAR, edge-dependent AR devices. And here, a UE is a generic term used in 3GPP for user equipment. You should consider it as a consumer device. So here is a list of use cases identified so far for which the mapping of media service architecture is required. They include messaging, AR content downloading for online shopping applications, for instance, extra conversational services, shared spatial environments, remote cooperation, as well as streaming of volumetric content. AR glasses contain various functions that are used to support a variety of different AR services as listed in the previous slides. But AR devices, they share some common functionalities in order to create the XR experience. And this figure provides a high-level overview of the relevant functions of such a device. So we have the AR/MR application in green, a software application that integrates audiovisual content into the user's real environment. We have the AR runtime in dark pink. That is a set of functions that interface with a platform to perform commonly required operations such as accessing controller, peripheral state, getting current or predicted tracking positions, as well as submitting the rendered frames. We also have the media access functions in yellow in the figure that contains a set of functions enabling the access to metadata that is needed for in the scene in order to provide an AR experience. And in the context of the studies, the media access function obviously uses the 5G system functionalities to access the media. We have peripheries that can be sensors, cameras, displays, and other functionalities on the devices. Those peripheries, they all provide the physical connection with the environment. And finally, we have the scene manager in blue that contains a set of functions that support the application, arranging the logical and spatial representation of a multisensorial scene based on support of the AR runtime. So as an illustration, this figure describes the mapping of the standalone AR device to the 5G media delivery architecture. The standalone AR device includes all the functions from the previous slides, the AR runtime, the AR scene manager, the media access functions, as well as the application that resides and is executed on the device itself. And all essential XR functions are available for typical media processing use cases. And this is the reason why the device is referred to as standalone AR, the STAR. I understand the interest from this workshop is likely to be on the scene manager, for which 3 main subfunctions are defined. We have the scene graph handler. That is a function that supports the management of a scene graph and permits interaction with the scene. We have the compositor, compositing layers of images at different levels of depth of presentation, and the immersive media renderers in charge of the generation, for instance, of 1 or 2 eye buffers for visual contents, targeting monoscopic or stereoscopic displays that usually relies on GPUs. And same here with the 5G Edge approach that breaks down some functionalities initially supported by the user equipment in the STAR device and that are shared now with the Edge or the cloud. And the AR runtime remains the same, but the scene manager is called lightweight as some subfunctions are moved to the network entity, such as the scene generation and composition. And same for the media access functions that are also split between the user device and the network, such as the split rendering. And those functions are handled via the 2 interfaces already introduced by Frederick M5 for the control plane between the media session handler and the media application function in the network, and the interface M4 for the user plane between the media client and the media application server. And this type of device is an edge-dependent AR device. That's why we call it EDGAR. This ongoing work still needs to refine the procedures and code flows for identifying the protocols and APIs upgrades. Content formats and codecs also need to be analyzed, as well as key performance indicators and QE parameters that are likely to be converted into media service requirements. So we will also need to use the findings of the study on edge processing architecture for streaming services in order to integrate them into our scenario. And that's pretty it. And now I'm handing back to Frederic for the next steps.
Yeah, I guess we've, thanks Jill, we've eaten all our time, but it's to give you a glimpse and of what lies ahead for us in release 18 in 5G Advanced. So maybe you can go to the next slide, Jill. This is the summary of the workshop we had for 5G Advanced SA4 tasks, and it's ongoing work. But the on the XR chapter, I mean, what we're looking towards doing is to define new immersive media types and formats definition, including the quality of experience metric for all of this. And with regards to services, XR and cloud gaming, we are trying to get a unified framework for all such new services, and that enables collaboration between the mobile network operators and the third-party service provider, including support for OTT. And then on the next slides, you will see the, in particular, I wanted to highlight the, as a result of the 5G STAR study that Gilles described, we expect new media formats for AR and MR upcoming in release 18. On the next slide, they are highlighted QSQ metrics and split rendering for FS for the XR applications, as well as XR real-time communications, XR streaming, and MTSI extension for XR conversational. I think there's also a chapter on haptics. That's probably on the next slide. So I thought this really matched the, I don't know where haptics is shown. It should be there somewhere. We have some stage 1 requirement for haptics that matches what was presented earlier on today. So it's very interesting that this work's happening in MPEG and Khronos. And then further extension on the 5G media streaming architecture to support the split rendering. So this last one is really an invitation for all interested to join. We will have another release 18 workshop on the 3rd of November, and we plan to agree on the content of release 18 until March next year. And that concludes our presentation. And sorry, Thomas, for eating a bit of time extra.
Thank you, Frederic and Gilles. Much appreciated. I will trade this in at some point in time, but it's always good. So let's have some quick questions for Frederic and Gilles on 3GP and 5G. Are there any? Neil, please.
Hey, that was a great presentation. Thank you. The just to reinforce what Brent was saying earlier, to Thomas's question, the work that we're doing at Khronos with OpenXR is not in conflict at all with all of the great work you're doing on the implementation level of getting AR over 5G to be working well. Have you looked at using OpenXR as a way of exposing all this good work into the developer community? We are getting momentum there. It would be great if we can add value to your efforts in that way, and explore whether any gaps that we would need to fill to provide that value to you.
Gilles,
yeah, I think I can answer to this. I mean, basically, when looking at some device architecture, there's still a need to break down each, I mean, to utilize each functional block and see what the candidate technologies are. And as far as I can say, yeah, I mean, OpenXR has been listed as a candidate technology. It is still to be checked what is in the scope of 3GPP and what is not. So what is really needed from us to from a 3GPP perspective to specify. Obviously, the connectivity aspects of the 5G device with the 5G network this is something that is fully under our scope and responsibility. Now, with regards to the device capabilities, for sure, for interoperability, we may recommend the support of certain format or rendering techniques, but we need to still to identify the frontier at which we will stop and say, well, this is device specific. And so my answer would be, as long as it crosses the 5G network and as long as some interoperability is required in terms of device support, this is something that should be addressed by 3GPP. But OpenXR is already documented as part of the existing technologies under consideration for our study.
Yeah. Okay.
Okay. Maybe
Anything
I have
else?
a question to, maybe I have a question on OpenXR.
Sure,
Then. Are there hooks in the API today with regards to connectivity?
That goes maybe to Brent and Neil.
Maybe to Brent, yeah. Are there hooks and functionalities to access to realize those split rendering use cases with distant?
Is Brent there? If not, I can answer. Brent is probably better. But if not, so the answer is no. And the reason and I think that's a good answer because it's all to do with abstraction. Right? OpenXR is just an API for developers to reach into an XR implementation. OpenXR hides everything to do with the implementation, and that's the value of OpenXR. It provides portability for application developers. So OpenXR, from the developer perspective, it doesn't care whether it's on 5G, and of course, all the excellent work you're doing is going to be essential to make that work. The value that OpenXR can bring is that you can just implement it on a 5G based system, and the developer doesn't need to know, ideally. But we, of course, if that's going to happen, then we need to make sure that the API is well formed for your use case.
Right.
But we believe it to be so. NVIDIA is working on stuff. Other companies are working on stuff where we can hide all the implementation details. So that's our goal. We would love to talk to you to make sure that is a possibility.
Right. I understand very well the ambition to hide this complexity to the application developer, but in particular OpenXR implementation with support for 5G connectivity, then there might be guidelines or recommendations on how to enable that connection and make sure that the interactivity and the latency is ensured.
Yes, I mean, if we do need hooks in the real world to expose some of the underlying capabilities of the platform to the application developer, for example, then that's certainly something that we could put in OpenXR extensions. But again, it would be great to talk about that.
So I would like to take the opportunity to jump in here in the interest of time, because I promised that we're gonna finish on time. Maybe I'm stealing 2 minutes from your day job or your family time. But I wanted to at least give the opportunity to have one slide to wrap up. And I know we don't have a lot of discussions, but I collected a few things which I identified. I believe we have seen there's complementary work happening across the different organizations. And I see there's many touch points, and touch points are conceptual, but they're also formalized, right? Like we have extensions. So we can basically do extensions here, or connectivity hooks and so on and so on. Overall, it seems to be that a collaborative effort, whatever collaboration means here, right? Well, what is the formalist and what is the exact points, is something that is beneficial, but the execution is not clear. I believe we have seen a few specific topics that maybe digested further, and these are just examples. I'm not making this like an exhaustive list, but glTF and the extensions done by the scene description. I believe this is a clear track. We're working together and we continue to do so. We have a method, and I think it was good to have the exchange. Generally, tools and implementation support, I believe that's worthwhile. I don't know if we can integrate 3GP, for example, in this context as well. would be interesting to understand how that could work. I believe clearly the Vulkan video and the VDI, there is some discussion that should worthwhile be continued. Generally, the topic of XR, extended realities, what happens in OpenXR, MPEG phase 2, and haptics. I think there is touch points here, a good discussion about the relation between haptics in MPEG and in OpenXR, and Frederick mentioned also 3GP has done some initiated some work on haptics. I believe it's good to understand how this works, but generally the topic of extended realities as part of the different groups is interesting. And then personally, I'm always interested in systems end-to-end workflows. And a typical example is a split rendering, and there's many different implementations of split rendering. And it seems to be that all groups have this somewhere in their mind. They have different expertise, and I believe one of the efforts would be really identifying how we can separate, collaborate, so divide and conquer these different aspects. I understand that there is challenges by collaboration. There is different timelines. There is different ways of operating, rules of publication, specification, IPR policies, memberships is different, interests. These are all challenges, but I still believe it's our duty to overcome some of those and understand if we can. So there's many opportunities, complementary expertise. We want to, at the end, we provide technologies for implementers and developers, and they should get easy access to these complex technologies, right? So it should be simple because it's not us to defining the experiences, it's other people. Joint promotion of work happening in organizations. How does it fit together? And also allowing that groups can focus on very specific issues where their expertise lies in. I just propose as next steps, and that's where I want to get maybe 2 or 3 minutes of feedback, continue the discussion, and create some kind of discussion platform for topics. And I don't know yet what is a good suitability, but that's what I have here. So maybe let me check if there's any quick feedback, especially Neil and Frederick, but also open to others as well.
I think that's a great summary. Well done. In real time.
Yeah, absolutely.
So, yeah, definitely continue discussion, and we can brainstorm on what the best platform should be. But yes, +1.
Okay, anything else, Frederick?
No, big thank you for this. I think at least this was extremely useful to me. I have the impression it was very useful to many of us, and looking forward to next steps.
Okay, and I would like to finish with a thanks specific to Neil and Frederick, as I said, making this happen. It was not a high-end conference. We planned this a bit on the fly. We all have day jobs, so I think it worked out relatively well. It takes some time from people, especially all speakers for the presentations, answering the questions, being open for discussion, staying on, and so on and so on. So thank you, everyone. I don't mention anyone explicitly now, so everybody should be included here. All the participants and for attendance, discussion, wherever. And what I did is I created also a bit on the fly a survey. Don't make the survey as something that is being binding or anything like this. We just want to get a bit of a feedback. What did work and not? Give us some feedback, and potentially also what would be forms for to continue the discussion. We will send out emails to the participants, and we will then also announce a bit what we could do next, what would be the results of the survey. With this, I would like to close the session and thank again and wish you a great day and hope to see you again, and next time hopefully in person. So thank you. The session is closed. Bye-bye.
Thank you, Thomas.
Thank you.
Thanks, Thomas. Bye, everybody.
Bye.